Hello everyone, today we are going over simplifying radicals. Simplifying radicals is something that we have done when we were in Algebra 1 and also a little bit when we were in geometry, and it also comes back for us in Algebra 2. So let's say you were given radical 45. This is not a perfect square, so when we put this into the calculator, we get a decimal answer. So we want to look for something that is a little bit simpler than a really long decimal. In order to simplify, we look for a perfect square that goes into our radicand. So 45 is radicand. The number under the radical is called a radicand. Now, in order to do this, what I usually do is I list out all of the perfect squares. So let's say 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, 16, 25, 36, and then 49, so on and so forth. So I know 49 is too big to go into 45. I start with 36. I ask myself, hey, does 36 go into 45? So what I do is I do 45 divided by 36, decimal, no good. 45 divided by 25, decimal, no good. So as you can see, this process takes a little bit of time. So there's also an easier way. We go to y equal, and then we put in our 45. Let me clear this out first. I put in my 45 and I divide by x because we're looking to find which number goes into 45 that is a perfect square. Then I go to my table. Ooh, everything went away together. Then I go to my table and I look for the whole number that has a perfect square. So I see 4 is a perfect square. Oh, it didn't register. My bad. Let's do it again. 45 divided by x. Okay, this is interesting. We will do it separately, no problem. 45 divided by x, and then, okay, third time's the charm. Let's see. Okay, so we're going to look at the positive numbers with 4. So we see 4 is there, but 4 times the decimal. We don't want that. 9 is a perfect square. 5 is not, but that's okay. We have one perfect square, and we go with that. So let's go ahead. This we can break it into square root of 9 times square root of 5, which gives us 3 radical 5. And that's it. That's our answer. Now, there are times when it gets a little bit interesting. So let's say if I have radical 72. So with radical 72, there are 2 perfect square that goes into it. One of this is radical, let's see if the calculator would be nicer to us this time. Y equal, let's say 72 divided by x, second table. So one of them is 4 and 18. Then we have 8 and 9. Okay, we want to look for like bigger ones. And I'm actually going to talk about why we look for that bigger one. So if I keep going, I feel like there was one earlier. There we go, 2 and 36. Now, radical 2 and radical 36, we can right away simplify it, which gives us 6 radical 2. But radical 8 and radical 9, we have to break that radical 8 one more time. And then this is 3, which gives us 2 radical 2, and then 3, which is 6 radical 2. So much work on the left side, but so much simpler on the right. So we always look for the bigger perfect square, not the smaller one. We want to go with the bigger ones. Now, the new thing for us in Algebra 2 is like we are getting introduced to variable in our underneath our radical. So let's say I have radical. Let's work with the ones we had already. 45 x to the power of 3. Now I know radical 45, I could break it into radical 9 and radical 5. So radical 9, radical 5. Now for this x to the power of 3, we need to find out how we can break it simply. The reason there's also another name for radical we are used to hearing is square root. Now, the reason we call it a square root is like this number, like it's invisible, we don't really write it. This index is a 2. And this number, we call it a power. I mean, we also call it exponent 2. There is a rule to rewrite these exponents with like radical. We call it power over index. So if I want to simplify it, I ask myself, hey, I have 3 over 2. I want to break it evenly. So one of them is much more simpler. So what I would do is write it as x squared and then x, which leads me with this is 3 radical 5, and then this becomes the exponent of 2, and the radical gets canceled out because technically this is x to the power of 2 over 2 power over index. So this is just x, and the radical x remains the same, which is 3x radical 5x. I took this, put it here, this goes here, and whatever is not simplified, I just put them mashed up together underneath the radical. Let's do another practice of this, just so you know we can see another way of doing this. Let's say we have radical 18 x to the power of 8. Okay. Radical 18, I'm sorry, we could break it into radical 9 and radical 2. Now for radical x to the power of 8, I could break it into like x to the power of 4 and x to the power of 4. I chose to be that way because our index is 2, and I want to break my exponents evenly into numbers that is easily divisible by 2. So for us, it would be 3 radical x, and then we get x squared times x squared, because 4 divided by the index of 2 gives me a 2, which leaves us with 3x to the power of 4, because x times x gives us x to the power of 4 because we add the exponents, and radical x. Let's say instead of x to the power of 8, it was 18x to the power of 9, then that would be a little bit tricky, like very small change. That would be that we have radical 9. Radical 2 still is there. Now, when we go to break the exponents for the variable, this is still x to the power of 4. Again, x to the power of 4, but the last one would just be a radical x, which gives us 3 radical. Oh, I made a mistake in the earlier one. This is 2 radical 2 x squared times radical x, which is 3x to the power of 4 times radical 2x. Now, instead of a square root, there are possibility that sometimes we end up having a cube root. So let's say we had cube root of 8. X to the power of 6. Now, cube root of 8, that we know we could put into the calculator. Let's see. Math, and then cube root is option 4, 8. That is a 2. That one is taken care of right away. Now, x to the power of 6, we can break that up into cube root of 3, cube root of 3. So that way, when we do 3 divided by 3 is equal to 1. So that means we have x to the power of 1 times x to the power of 1, which is equal to 2x squared. Okay, that was simplifying with our variable. Now, when it comes to adding and subtracting radicals, we actually follow the order of like when we are combining like terms. So when we were combining like terms, we had to make sure that our variables was exactly the same. So if I had 2x plus 2y, we couldn't really do much with it because there is no like term. Like term means we have to have the same exact variable and same exact exponents with those variables. So for this one, we don't really have that. But let's say if I had 2x plus 2x, that would be equal to 4x because we had that like term. If I had something like 3x squared plus 8x, we could not combine that because one of them has an exponent of a 2 and the other one has an exponent of an invisible 1. So not a same one, we cannot combine it. Now, for if it comes to like our radicals, we look for if it has the same radicand. So let's say I had radical 18 plus radical 72. We had simplified this earlier. This will be radical 9 and radical 2. This is radical 36 and radical 2, which is 3 radical 2 plus 6 radical 2. Both of them have the same exact radicand. So we just add the coefficient 3 plus 6, which is equal to 9. That gives us the final answer is 9 radical 2. And this is the same idea with like adding and also with subtracting. So let's say if I had something just a tad bit different. Negative 8 radical 27 minus 2 radical 108. So now I will start with breaking up my, simplifying my radical. And 108 is radical 36 times radical 3. Negative 8 times 3 radical 3, because we cannot forget the original coefficient that was there, which gives us negative 8 times 3 is negative 24 radical 3. And then let's move on to the next one. 2 times, all of these are being multiplied in between, 6 radical 3, 6 radical 3. Now, 2 times 6 is not 6. 2 times 6 is 12. Now that we know that we have the same exact radicand, 3 and this 3, so that would mean that we just combine our coefficient. And in this situation, we are subtracting them. Negative 24 minus 12 would give us a negative 36 radical 3. Okay, that was with adding and subtracting.